You never know what's going to cause the next great discovery to be made. Is it a eureka moment in the middle of the night? Is it some small inconsistency in the measurement that you made? Isaac Asimov famously noted that the greatest discoveries in the history of the world weren't somebody burning the midnight oil saying eureka. It was somebody looking at some data and saying, that's odd. So consider that in the late 1800s, classical physics was riding high. What is classical physics? It's Newton, it's electricity, it's magnetism, it's all of these sort of basic laws of physics that were established between the 1600s and the 1800s, all right? Definitely before the quantum and before relativity and all these exotic theories of the universe that defy every bit of common sense you could possibly bring to bear. So there's some well-known scientists at the end of the 1800s, and they were sure that there were no more major discoveries to take place in the field, and that physics would soon end. There were just a few messy clouds on the horizon that some better research would resolve. Would say these these differ from each other. Do the experiment again a few times and that'll all come out just fine. Coming out of the 1800s, however, those small clouds turned out to be more like sort of chinks in the armor of classical physics, which eventually opened a door into a century of mind-blowing modern physics that transformed the world. Not only the world of physics, but geopolitics as well. The simple introduction of E equals mc squared as the foundation of all of our nuclear arsenals, how they generate energy. So small things that don't quite work. Some of them get resolved with better data, others don't. They lead to deep and new understandings of the universe. And so in that spirit, I bring to you a story, something we call the Pioneer Anomaly. There are two spacecraft, Pioneer 10 and 11. They were launched in 1972 and 1973. And they were destined to take a tour of the planets and escape the solar system altogether. And the way you do that is, because our rockets aren't big enough to give it that much energy. So they launch and they come in behind a planet and they fall towards it, and the orbit of the planet catches on to the space probe. And then you do a sort of a gravitational slingshot, flinging it forward with extra energy. When you do that for a couple of planets, you can have enough energy to have those space probes escape the solar system altogether. They were the first ever pieces of hardware to achieve this feat. And because of this fact, we had affixed on their sides a famous plaque of pictograms. It showed, among other things, an unclothed male and female human form. And the male, you may remember this from the day, and the male had an arm raised, presumably a sign of peace. That assumes that this is a sign of peace to aliens, of course. But on this plaque, there was a map that showed where the craft came from, which is essentially the return address of the solar system in the galaxy. And not only that, it showed some other basic scientific insights that we've gleaned as a species. So all of this is in case the aliens from another star system found the craft. It would allow them to learn basic facts about our species. And I'm reminded, there was a comic shortly after these spacecraft did their thing, and they were well publicized. There was a comic, and it showed aliens who had come upon the Pioneer craft. And they're looking at this picture that we sent on the side of the craft, and these aliens are dressed in tuxedos, by the way. And one alien turns to the other and says, they're just like us, except they don't wear clothes. It was a stupid comic, but I'll never forget it. But anyway, these plaques represented the first ever attempt to communicate with another species using pictograms and hardware that they might come upon. Now, Here they are on their way out of the solar system. We expect them to slow down. We know they're going to escape, but whatever speed they have, we expect them to slow down as they climb out of the sun's gravitational embrace. Now, since they have enough energy to escape entirely, they'll slow down, but never slow down to zero. Okay, that's fine. Here's the problem. The actual deceleration we measure is greater for each craft than what we calculate it should be after accounting for all the possible forces that could slow down the craft. That is the Pioneer anomaly. The effect is small, but it's persistent, and every attempt to understand its cause has failed. The effect became measurable about 8 years into the journey, but it was not studied in detail until about 1994. Now, we haven't communicated with the Pioneer craft since 2003. They're too far away now for signals to be exchanged. But we have data over a 23-year period from 1980 right on up through 2003. And that baseline of data continues to be studied. Now, consider, we've never before measured the force of gravity in the solar system with such precision over such distances for such a long period of time. So this constitutes a new experimental frontier. In physics, if you perform an experiment that's never been performed before, you almost expect something new to show up. You expect it, because no one has done it before. It's looking in a place you had never had the occasion to look to understand the behavior of nature. All right, so what's at cause here? Is the sun misbehaving? First, you blame the engineers. That's what I would do. Blame the engineers. It's like, look, have you looked at all the possible onboard sources of what could interfere with the acceleration of this craft, okay? Have you looked at any possible sort of outgassing of fuel cells or fuel tanks? Or double check, triple check. Bring in the designer of the craft. Do you have a model of it here? Let's check that, okay? All of this has been done. All of this has been done. And all those sources of errors have been removed. We're pretty sure. Okay, so we ask ourselves, has this experiment found the limits of our current theories of gravity and motion? Or is there still some engineering problem that even the designers of the craft have not figured out yet? What we know is that this problem exists for both Pioneers, and they're not headed in the same direction. They're at like 90-degree angles to one another. They both have this extra deceleration. The Pioneer anomaly remains unsolved to this day. Do we know if it'll ever be solved? Because there's not another experiment right now ready to double check it. We're kind of stuck with these data for now. But I can tell you, if it never gets solved, and it is an anomaly, this is a piece of information that we're going to have to hold on to, not dust it under the rug, not just keep blaming the engineers. At some point, you have to blame nature. And when you get enough of those occasions where nature is misbehaving, you know it's time to come up with a new theory of the universe. And that might just be what awaits us. You know, 85% of all the gravity we measure in the universe comes from a source about which we know nothing. We call it dark matter. But since we're fundamentally clueless, we don't know what it is, okay? The dark matter is just a placeholder name We could easily have just called it Fred, all right? In both cases, we don't know what it is that's causing it, all right? We have no idea. Dark matter was discovered in 1933. It's been around for a while. It was discovered by an irascible astrophysicist named Fritz Zwicky. He was Swiss-born, but spent most of his professional life in America, in fact, at Caltech in Pasadena, California. What he did was he studied a large cluster of galaxies, happens to be called the Coma cluster. It has 1,000 galaxies in it. Whole galaxy. A galaxy has itself billions of stars, so this is a massive structure in the universe. And all these galaxies are bound together by their mutual gravity. And what he found is that the speed that these galaxies are moving within the cluster is faster than the collective gravity of each galaxy can sustain. In other words, at the speeds he found them moving, the galaxies should have flown apart from one another long ago. But they're not. They're bound together. They're still bound together. They didn't fly apart. He proposed that there's some missing mass that must lurk somewhere within the cluster whose extra gravity he was tracking. Now, this result turned out to be true for every single cluster ever measured ever since. Back then it was known as the missing mass problem. Today, we call it the dark matter problem. Let's fast forward. 1976. Carnegie astrophysicist Vera Rubin. She was studying the rotation of spiral galaxies. We're a spiral galaxy, the Milky Way. And what she found is that they were rotating faster than the known mass within the galaxy should allow. Dark matter, it turned out, was not a problem unique to galaxy clusters. It was a problem that revealed itself even within galaxies themselves. Could it be dark clouds, black holes, dark planets, anything dark? No, 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 and no. If it has substance, then it cannot be made of anything familiar. Familiar materials, they absorb, reflect, refract, and otherwise interact with light and other materials. But this stuff doesn't interact with anything at all, not even itself. It only reveals itself to us through its gravity. It is a fundamentally different thing going on than any possible measurements that our own familiar materials would reveal. So, you could ask, could it be an undiscovered family of particles that barely interact with our kind of particles? Sure, why not? In fact, that's the odds-on favorite scenario. And top particle physicists today are working on that. Could it be a failure in our concept of gravity? In other words, do we need a new theory of gravity to account for it? Unlikely, but we've got top gravity theorists that are working on that one too. They call it MOND, Modified Newtonian Dynamics. Seems like whatever is your specialty, you think the solution resides within your expertise. Reminds me of the old adage, if we were hammers, would the dark matter problem look like a nail? You know what my favorite possibility is? Maybe the dark matter is the ordinary matter of an 85% more massive parallel universe influencing ours by gravity leakage from one universe to another. I like that one. If so, it would be the first evidence of other universes. And yet, the evidence was there all along. You know, dark matter is the longest standing problem in modern astrophysics, and it persists to this day. As if one profound mystery of the universe is not enough. Recently, dark matter was joined by dark energy as one of the most profound sources of ignorance the astrophysicist faces today. In the late 1990s, teams of researchers led by Saul Perlmutter, Brian Schmidt, and Adam Rees discovered that the expanding universe, itself discovered by Edwin Hubble in the 1920s, was accelerating. That turned out to be a Nobel Prize-winning measurement. This force that's making it accelerate, we call it dark energy. But since we don't actually know what it is, we could just as easily call it Barney. All right, that's what I want. Dark matter I'll call Fred, dark energy Barney. It doesn't matter because they're just placeholder words to accommodate our ignorance. You don't want to read too much into those words. So, here's how it works. If the collective gravity of all the galaxies in the universe were all there was, then the expansion of the universe should be slowing down, not speeding up, because gravity is an attractive force, resisting the expansion. What we found is that there's a mysterious pressure operating in the vacuum of space, and it's combating the gravity and winning. We don't know its origin. We don't know what it is. We're not even sure of its long-term effects. Turns out, Albert Einstein, after he published his new theory of gravity in 1916, that's, of course, the general theory of relativity, he noticed that it predicted a universe that should either be contracting or expanding. Now, that's odd. How could everything you know, how could the universe do anything if it is everything? This was a profound scientific and philosophical dilemma. Unthinkable concept. And if it's expanding or contracting, compared with what? And so Einstein added a mathematically legitimate term to his equations. That term allowed him to stabilize the collapsing influence of gravity in a way to hold up the universe against its wishes. And that way he could keep the universe the same size, whatever size that was. Within just a few years, however, after Edwin Hubble showed that the universe was indeed expanding, Einstein rapidly withdrew the stabilizing term from his equation. You know what he called it? He called the introduction of that term the greatest blunder of my life. He knew, or he felt deep inside, that that term could not be anything physical. There's nothing in the universe that repels matter. Not on large scale. A magnet can do it, but on large scales, there's no known thing that could repel matter. So this term that he added to his equation, he was very uncomfortable about that. That's what left him to call it the greatest blunder of my life. Turns out, the measurement and existence of dark energy is precisely that term in his equations. What that term in his equations do is exactly what we see dark energy doing in the cosmos. So, in fact, Einstein's greatest blunder was saying that the inclusion of that anti-gravity term was his greatest blunder. Isn't it great to be so smart that you're right even when you're wrong? So, here's what you do. You take the energy contained in what we call dark energy, and it's 70% of all that drives the universe. Include with that percentage the dark matter, and we are driven to the humble, mind-blowing conclusion that 96% of all that is the universe is not anything we even remotely understand. 96%. And that all of our laws of physics, everything we know, love, interact with, and understand, or even can predict anything about the future, that falls into the 4% that remains. Now, Actually, it gets worse. Our most successful theory of the universe, quantum physics, allows you to calculate what you might expect to be the energy contained in the vacuum of space. We can do that calculation. It allows it. It predicts that there should be energy there. All right? We do the calculation. Quantum physics, it's never been wrong. It's our best understanding going. When you do that calculation, the answer you get does not match reality. The answer you get is off by a factor of 10 to the 20th power. That's a 1 followed by 120 zeros. Now, that's just embarrassing. I'm sorry. All right? We put forth our best theory to our biggest problem, and it gets us nowhere. In fact, it is the biggest mismatch between theory and observation that there ever was in the history of science. That's our state. That's our state of the science today. So, we are not only ignorant, our best theories in the universe can't guide us. So, I think that means we're driving blind. If you add together sort of the three kinds of things that occupy the universe, the familiar matter, that's what we're made of and what our telescopes detect. The dark matter, that's the source of 85% of all the gravity we see in the universe, and we don't know what's causing it. And the dark energy, the stuff that's making us accelerate against the wishes of gravity. Each one of those components creates a curvature of the fabric of space and time, just as prescribed by Einstein's general theory of relativity. If you add those curvatures together, what you find is that they create a universe that is perfectly flat. Flat. Now, that's not the only shape the universe could have had. The universe could have negative curvature, and if it did, that would have we would have a saddle shape. And a negatively curved universe has a net positive energy. The universe is neither a spherical shape, the shape of a ball. That would be positive curvature, having net negative energy. Now, another way to get insight into this is to think about the energy of orbits. An object in orbit is gravitationally bound to what it circles. And bound orbits have negative gravitational energy. That's how we describe this system. Increase the elongation of the orbit by pumping energy, giving more speed to the object, and the circle distorts and becomes an ellipse. Give it even more speed, the ellipse gets more and more elongated. There's just the right amount of energy, just the right amount of extra speed you can give this object so that it goes so far away it never circles back. In fact, it escapes to infinity. At that point, that object and the system and the orbiting object and the object around which it formerly turned has zero total gravitational energy. And that path is formally called a parabola. Give the object even more energy, then it gets to infinity and keeps going. That has net positive energy, and we call that trajectory a hyperbola. Now, you've actually seen these shapes before at home. Take a flashlight. All flashlights have a cone of light that emerges from them. If you take it and aim it straight at a wall, it'll make a perfect circle. Take it and tip the angle just a bit. That circle distorts and you get an ellipse. Tip the flashlight so it's parallel to the wall, and you'll see the shape on the wall and it'll take the form of a parabola. Angle it a little more, it opens up even further and you get a hyperbola. Try that at home. So, these are what we call conic sections, intersections of a cone of light. And they relate to orbits and they relate to the energy that those objects have. Now, if your space-time is flat, just as if your orbit were a parabola, it means The universe, the entire universe, possesses zero net total energy. Think about that. If the shape of the universe were anything else, positively curved or negatively curved, it would not have zero energy. It would have negative energy or positive energy. We have zero net total energy. Now you're wondering, is that good or bad? There's a silver lining to this. What it means is that you can create the entire universe out of nothing because nothing has no net energy associated with it. Had the universe been endowed with either negative or positive energy, we'd be forced to confront the questions of what was the original source of energy that begat the universe? And if it had some amount of energy, why is it that amount and not some other amount? The fact that we live in a zero energy universe bypasses that line of questioning. And does it leave us content in our emptiness? Perhaps. But we're no less enlightened by the ignorance that led to it. You know, while all this is going on in the universe, there's something that I think about often, and it's the fact that the Milky Way, the galaxy in which we live, is actually on a collision course with the nearest large galaxy to us, the Andromeda Galaxy. In fact, pictures of the Andromeda Galaxy are what we use to show what our Milky Way might look like from the outside, because it's kind of hard to see what we look like since we're in it. All right, we see stars right in front of our noses, we see these gas clouds, but the grand design spiral pattern that spiral galaxies are so proud of, we see that in the Andromeda, we infer that for us. Okay, so we have several 100 billion stars in our midst. So does the Andromeda Galaxy. Andromeda Galaxy is about 2 million light years away, and we're on our way towards each other. It is a collision impending. It will be a train wreck. Think about it. Here's every star in our galaxy attracting every other star orbiting the center of our galaxy where there's a supermassive black hole. That system is falling towards another system that also has several 100 billion stars all attracting each other. As they get closer and closer and closer, just imagine this, all right? Every star feels every other star's gravity. And as they merge, with the motions combined with it, stars get flung hither and yon. There'll be stars that'll be kicked out of both systems and will become lost to intergalactic space. The two black holes, we've got a black hole, they've got a black hole. They're going to be making a beeline for each other. They will feel each other's effects, okay? And if we're not in a direct collision course, even if we're to the side of each other, we will go into orbit around each other. And those black holes will eventually coalesce and make one bigger than either one started out to be. Eventually, our two galaxies will become one, a big, fat, double galaxy. And given enough time, you would have no trace that we started out as two separate systems, separated by 2 million years. 2 million light years, that is. Oh, by the way, a light year is about 5.8 trillion miles. See, that's why we just call them light years. It's easier. All right, here's what's interesting about that collision. These two galaxies, we think galaxies have collided all the time. We see images of galaxies that are badly disturbed. And in the early days of this exercise, we just thought they were irregular galaxies. In fact, that was an official classification for them. Until there was an astronomer who said, wait a minute, this was his exact words, a wrecked Lexus is not a new kind of car. It's just a wrecked Lexus. So if you have a galaxy that's badly disturbed looking, Maybe it was an ordinary galaxy that's in the middle of a collision. So we looked around the universe and we found galaxies in all stages of collapse towards each other. You can practically make a timeline of what our collision with Andromeda will look like based on the collection of all the galaxies we have out there in the universe that are in the act of colliding with each other. And so, this is in our future. The problem is, we will collide with Andromeda after our sun dies. After the sun around which we orbit expands to become a red giant and engulfs the orbit of the Earth, rendering us a charred ember soon to become vaporized. So we need to find a way to move to another planet or another star system to watch this happen. But then when we watch it happen, if a star comes too close, you can have a flyby looting of the planets that belong to one star get stolen by another because stars will be flying back and forth. So, it'll be an exciting time for Earth when that happens. Or it'll be an exciting time for any civilizations alive to watch it. What we don't know is whether Earth will survive that. Will we be among those flung into intergalactic space? Will we fall towards the super duper massive black hole that now occupies its center? Or will we find a new home around a new star that is perhaps just born, giving us a new lease on life for the apocalyptic civilization that follows ours?